How do you do? The theme of the fifth lecture is Kirchhoff's rules and the electric conductivity of solid bodies. In particular, we will consider the electric conductivity of metals. At the end of this lecture, you will learn about branched circuits, Kirchhoff's rules, the classification of solid bodies by their electric properties, the nature of the current in metals, Tolman and Stewart experiments, and the Mandelstam and Papalexis experiments. Classical theory of conductivities of the metals. To understand this lecture, you will need the following vocabulary. Branched circuits, разветвленная цепь, тармақталған тізбек. Loop, замкнутая цепь, тұйықталған контур. Junction, узел, түйін. Sign convention, правила знаков. Insulator, диэлектрик, оқшаулағыш. Theory of conductivity, теория проводимости. Crystal lattice, кристаллическая решетка и кристаллдық тор. Branched circuits. Resistors in many electric circuits cannot be reduced to simple series parallel combinations. And that is why Ohm's law cannot be applied for such complex circuits. There are two techniques developed by German physicist Gustav Robert Kirchhoff that are used to solve complex circuits. These techniques are known as Kirchhoff's rules. There are two terms that are used in complex circuits. They are junction and a loop. A junction in a circuit is a point where three or more conductions meet. Junctions are also called branch points or nodes. A loop is any closed conducting path. Here are figures that demonstrate these notions. So by the loop, we mean a closed conducting path. There are, in this scheme, the first loop conducting path, the second conducting path, the third conducting path. And in the second figure, we have the first conducting path, that is the second conducting path, the third conducting path, and the fourth conducting path. And here in this picture, A and B, they are junctions because there are three, 1, 2, and 3. Here, 1, 2, and 3. Three wires or conductors meet at this point. That is why A and B are called junctions, while C and D are not junctions. They are not junctions because there are only two conductors meet. It is less than 3. And here, so the same A, B, D, and C, they are junctions, while F and E, they are not junctions. Kirchhoff's first rule is the junction rule. The algebraic sum of the currents that meet at a junction, it is equal to 0. So when we say algebraic sum, we mean that we should obey the sign convention. The currents that enter the junction, they are taken to be positive. And so I1 is positive and I2 also positive because they enter the junction. And the current I3 I3 is negative because it leaves the junction. And that is why the algebraic sum of these three currents is written as I1 plus I2 minus I3 is equal to 0. So the Kirchhoff's first rule is based on the conservation of electrical charges. Kirchhoff's second rule. The Kirchhoff's second rule is the loop rule. The algebraic sum of the potential differences in any loop, including those associated with electromotive forces and those of resistive elements. This sum must be equal to 0. So in mathematical symbol, we write that is the sum of all potential differences along the loop or the complete circuit, including the potential differences associated with the resistive elements, and the potential difference associated with the electromotive force. So we say about the algebraic sum of these potential differences. It is, again, here we should obey the sign convention for the loop rule. The loop rule states that the electrostatic force is conservative. When we go around a loop, measuring potential differences across successive circuit elements, then if we begin from this point and we go through these elements and again return to this point, then we must find that the algebraic sum of all these potential differences is 0. Because if we return to this point, we should have the same amount of the charge of the potential, and the final potential will be equal to the initial potential, and that is why the sum will be equal to 0. By their electrical properties, solids are divided into 3 groups: conductors, semiconductors, and insulators. Conductors are solids that have good electrical conductivity. All metals are known to be good conductors. Their conductivity depends on the number of valence electrons of their atoms. And these electrons are loosely connected with the nucleus of the atom, and that is why they are free to move through the lattice, the crystal lattice of the. So let us make the summary of our lecture. Today we considered Kirchhoff's first rule for the junction rule, Kirchhoff's second rule for the loops rule, and then calculation of electric circuits requires obeying the sign convention for the loop rule. Then we considered the electric properties of solid bodies, in particularly metals. And Tolman-Stewart experiment proved the charge carriers inside a metal were electrons. According to classical theory of metals, electrons of conductivity behave like molecules of an ideal gas. And the average speed of thermal movement of electrons can be determined by the formula of Maxwell for the average speed of molecules or atoms of an ideal gas. But the classical theory of conductivity does not lead to correct quantitative results. And this discrepancy was conceded or overcome in the quantum theory, considering wave properties of microparticles. The lecture is over. Thank you for your attention.